This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to talk about reflection and refraction of light. But it's also important to know that much of what we talk about here also applies to sound, and specifically ultrasound. And so I'll talk about that more as we go through the presentation. The first thing we need to understand is something referred to as the ray model of light. What the ray model of light says is that light travels in straight lines, and we call those rays. This picture kind of illustrates it. Here we've got a room with some dust in it, and you can literally see that the light is traveling in straight lines. In fact, you'll notice if the light didn't travel in straight lines, then this window wouldn't cause the reflection that we see down here on the ground. So I think it's pretty understandable for us that light does travel in straight lines. But how does this relate to the wave concept that we've been talking about? Well, I want to show you how a ray, which shows us the direction that the light is moving, relates to the actual light waves. To do that, let me first draw a picture of a transverse wave. So here's a transverse wave. And now I want you to think about it three-dimensionally. So think about this like as a wave on the water, where we're kind of looking at it from the side, but it extends in or out of the video. And now imagine that you just marked the crest of each wave. Now again, those aren't really dots, but they're lines because that wave is three-dimensional, not just two-dimensional. Now imagine you looked at that from up above, and what you would see is these lines. So the lines here represent the crests of the waves, and we call those the wave fronts. So in other words, the distance between any two adjacent wave fronts is just the wavelength of the wave. Again, because we know that light is a transverse wave, it makes sense that our wave fronts are perpendicular to the direction that the wave is actually moving. The next thing we need to do is we need to define what it means when we say that something is normal. In math, the word normal is used to mean perpendicular. And we're going to be talking a lot about a line that is normal to the surface. So here we've got a surface, and we'll see that for us this could be either a mirror or a transition between two different materials. But the normal to the surface is simply a line that is perpendicular to the surface. Okay? And you'll notice that nothing is really there. It's an imaginary line. But it's going to be useful for us as we look at both reflection and refraction. Well, we're now ready to use the two things we've just talked about, that light travels in straight lines that we can represent by rays, and this concept of the normal, to learn the law of reflection. The law of reflection is probably the simplest scientific law that you're ever going to learn. It basically says that if we have light coming in, so our light is coming in this direction, represented by that ray, and down here we have a mirror, that when that ray hits the mirror, it's going to come off with the same angle that it came in with. Notice that these angles are going to be measured. So we measure angles relative to the normal. So that means that this angle here we would call theta 1, and what the law of reflection tells us is that that ray will come out with an angle theta 1 prime, where theta 1 is equal to theta 1 prime. By the way, we call this incident ray that creates this angle. So we call the angle of incidence. And we call the angle for the reflected ray the angle of reflection. Okay, so reflection is pretty straightforward. Whatever angle the light comes in with relative to the normal is the angle that it goes out with. There's a little bit more to reflection, though. And what we want to talk about now is the difference between diffuse reflection, which is what everyday objects do, and specular reflection, which is what mirrors do. So let's start out by talking about diffuse reflection. Everyday objects are not smooth. Even something like the surface of a table is not mirror smooth, but it still has some roughness to it. And so what that means is when the light comes in and hits it, and here we've got a number of rays coming in, so that just shows us light coming in at some angle to the surface. Since the surface is not smooth, even though the law of reflection is followed, depending on what the surface looks like at the point where the light interacts, the light might go off in this direction, or here you'll notice it might go off that way, here it might go off that way. And so what that means is when light hits an everyday object, the light is reflected in virtually every direction. Now, if you think about it, that's why we can see objects. Imagine that you've got just one light bulb in a room. So here we've got our light bulb. And our light bulb is putting out the light that is shown by those rays. If the light didn't get reflected off basically in every direction, then we wouldn't be able to see that object from every direction. But you'll notice that no matter where we are, whether our eyeball is over here, or whether it's over here, or whether it's over here, we're going to be able to see that object because the light is being reflected off in virtually every direction possible. Now with specular reflection, which is what a mirror does, since the surface is perfectly smooth, so let me just write here, surface is rough. Even when it appears smooth, like the top of a table, it's still not really smooth. Whereas for a mirror, the surface is perfectly smooth. And that means that when light comes in, like this, since the surface is perfectly smooth, the angle that the light goes off with is going to just be the same for each ray because they're all hitting just that flat, smooth surface. What that means is if you put your eyeball right here, you couldn't see anything because no light is coming into your eye. So you wouldn't see the light. Only if your eyeball were up here would you be able to see that light being reflected. So again, everyday objects, the light essentially gets reflected off in every direction because the surface is rough. Mirrors are a special case. That's specular reflection. Because they're perfectly smooth, the light only comes off at an angle that is directly related to the angle of incidence. We're now ready to talk about refraction. And the first thing that I want to say is that refraction also happens with sound waves. We didn't talk about it when we covered sound waves because I knew we were going to talk about it now. But let me remind you what we did talk about with sound waves. We said that when a sound wave is sent in and it gets to the interface between two different mediums, that our incident ray splits and some of that sound is transmitted and some of that sound is reflected from the interface. And of course, that's very important to the whole concept of ultrasound, as we talked about in that video. You'll notice that when we talked about that, I always had the sound coming in perpendicular to the surface. In other words, along the normal. And in that case, the reflected sound comes straight back and the transmitted sound goes straight in. But it turns out that if the sound is coming in at an angle, then we get refraction, just like we do for light, which is what we're about to talk about. So what we want to figure out is what happens when light goes from one medium to another. For example, let's say that this is air up here and this is water down here. So at the interface, the first thing that we're going to see is that some of the light is going to be reflected. And so that's the law of reflection, as we've talked about, just like we did here with our sound waves. But some of the light will be transmitted into the water, and that's the refraction. If we look at what happens, what we notice is the frequency of the wave doesn't change. Remember, the frequency is determined by the frequency of the vibration. So once that wave is created, the frequency stays the same, with the exception of the Doppler effect if the source is moving. But otherwise, the frequency doesn't change. But we've said that light goes slower in materials like water than it does in air, and so the speed of the wave changes. Well, since v is equal to lambda f, if f is constant, then notice that if the speed goes down, the wavelength is going to have to go down. So both decrease as we go from air into water. Because of that, you'll notice that since the wavelength in the air is bigger than the wavelength in the water, the beam actually has to change direction. In other words, our incoming rays and the rays that are transmitted will be in different directions. And that's because the wave fronts have to be perpendicular to the ray. So the light has to actually change direction at the interface. And that's what we mean by refraction. Now again, the same thing is true for sound waves. And so that's part of the complexity of using ultrasound. If the sound beam is going in at an angle relative to the interface, the transmitted wave is going to change direction. Okay, so we want to be able to figure out how this angle, theta 1, is related to this angle, theta 2. Again, this would be theta 1 prime, the reflected angle. Before we can do that, we need to look at the concept of the index of refraction. The index of refraction, which we use the letter n to represent, is just the ratio of the speed of light in a vacuum to the speed of light in the material. And so let's look at some of these different values for n. You'll notice that by definition, the index of refraction of a vacuum is 1 because we'd just be taking c divided by c. Notice that for air, it's almost 1. And in the previous video I said we're going to assume that the speed of light in air is the same as in a vacuum. And so you'll see that's good to many digits. And again, that means we're just going to use c to represent the speed of light in air as well. In water, you'll notice that the index of refraction is higher than 1. Notice why that is. If v is less than c, so if this number is less than this, then that means n is going to be greater than 1 because we're dividing a bigger number by a smaller number. Therefore, the index of refraction of any material is always greater than 1. All right, let's do an example with this. What is the speed of light in glass if the index of refraction of glass is 1.5? Well, we've got our equation that n is equal to c over v, and we want to think about what it is we're trying to solve for. We're trying to solve for the speed of light in glass. That's v. So I'm going to multiply both sides by v. That gets rid of the v on the right. And now I've got v times n is equal to c. I'm going to divide both sides by n, and I get that v is equal to c over n. Now I just need to take the speed of light, 3 times 10 to the 8th, divide by n, which is 1.5, and you'll notice that what I get for an answer is 2.0 times 10 to the 8th meters per second. All right, that's the first part of the question. The second part says, if light with a frequency of 4.5 times 10 to the 14th hertz passes from air into glass, what is the wavelength of the light in the two materials? Well, now we're just using our equations for the speed of the wave. We want to start out with the speed in the air. Remember, we're assuming the speed in the air is the same as in a vacuum. So we're going to use c is equal to lambda f. And here we want to solve for lambda. So we'll divide both sides by f. And we get that lambda is c over f. So that's the speed of light in air, or a vacuum, which is 3 times 10 to the 8th, divided by our frequency, which is 4.5 times 10 to the 14th. And if you work that out on your calculator, you should get that the wavelength in the air is 6.7 times 10 to the negative 7th meters. Now, to figure out the wavelength in the glass, we now have to use our second equation here. We've got v is equal to lambda f, but we want to solve that for lambda, so I'm going to divide both sides by f. Therefore, lambda is equal to v over f. So remember, the frequency doesn't change, so it's the same frequency, but we're now dividing into the speed in glass, not the speed in air. And that was 2 times 10 to the 8th. And we're going to divide that by the same frequency of 4.5 times 10 to the 14th. And if you do that, you should get 4.4 times 10 to the negative 7th meters. So again, when light goes from one material, like air, into another material, like glass, remember that it's the speed that changes and the wavelength changes, but the frequency does not change. So let me just make a note of that. V and lambda change. F is constant. Okay, now we're ready to get to the last thing we want to talk about, which is Snell's law. And this is what allows us to figure out what is the angle of the refracted ray. Remember, the refracted ray is the part of the light that goes into the material. That's like the transmitted sound wave that we talked about when we were looking at sound waves going from one material to another. So in fact, I'm just going to write down transmitted just to remind you of that. Okay, so we call the angle of incidence theta 1, just like for reflection. Remember, our reflected ray is theta 1 prime, and that's just the same as theta 1. But now what we want to find is theta 2. What is the angle of the ray in the water? Now, we could also look at this. If the light originated in the water, then this would be theta 1. Some of the light would be reflected at the surface. And so that's an important concept both for sound and light. Remember, whenever sound or light goes from one material to another, from one medium to another, some of the energy is always reflected and only some of the energy is transmitted or refracted into the second medium. And so this would be theta 2. Remember that we're always measuring our angles relative to the normal. Okay, so here is the equation that tells us how theta 1 and theta 2 are related. So let's try this out. Before we do this, just like when we were using a cosine in one of our Doppler effect formulas, we've got to make sure that our calculator is set to the right mode. And so this slide is one that you saw in the Doppler video as well. We want to go in, click the mode button, and then make sure that degrees is highlighted. Okay, so we need to be in degrees. So once you're done, it should look like this. All right, let's see if we can figure out how to use this formula. So this problem says light makes an angle of 40 degrees with respect to the normal. So theta 1 is 40 degrees as it goes from air into water. What is the angle of the reflected ray? So that would be theta 1 prime. And what is the angle of the refracted ray? That would be theta 2. Well, let's answer the easy part first. We know that theta 1 and theta 1 prime are the same. And so theta 1 prime is just going to be 40 degrees. Okay, so that's easy. Some of the light gets reflected, some of it gets refracted. Okay, so now how do we use this formula? N1 sine theta 1 is equal to N2 sine theta 2. We can see that what we're trying to solve for is theta 2. Now, unfortunately, that theta 2 is trapped inside this sine function, but I'm going to show you how we deal with that. The first thing we want to do is just solve this for sine theta 2. So let's divide both sides by n2. Get rid of that so that we have sine theta 2 is equal to n1 sine theta 1 divided by n2. And now we're going to plug in the numbers. So sine theta 2 is equal to n1. So this is material 1, this is material 2. So air has an index of refraction of 1. We want the sine of the angle of incidence, which is 40 degrees. And then we want to divide that whole thing by 1.33. So I've got now the sine of theta 2. And if we do the math, well, let me actually just write that again. 1 sine of 40 divided by 1.33. Okay, so now we're going to do that math, and we get that sine theta 2 is equal to 0.483298. And there are more digits, but that's enough. What we now need to do is take the inverse sine, which is referred to as sine to the negative 1 of that answer. And the reason for that is if we take the inverse sine of sine theta 2, we just get theta 2. So we have to take the inverse sine of this number. Okay, how do we do that? Well, first of all, let me put down the answer. What you should end up with is theta 2 is equal to 28.9 degrees. But my guess is that many of you haven't done this before in a calculator or haven't done it in a long time. So I want to show you step by step how we do it. You'll notice that on my calculator screen, I have the calculation. So again, we had the sine of theta 2 is equal to 1 times the sine of 40 degrees divided by 1.33. So notice here I literally typed that in. I did the 1 times the sine of 40 divided by 1.33. And my calculator gave me this answer. Okay? And so that's how I know that sine theta 2 is equal to 0.48329 dot dot dot. Okay, so now how do I get the final answer for theta 2? It's actually really easy. You'll notice this is inverse sine right here. Sine to the minus 1 is inverse sine. Let me just make a note of that. So the way we write inverse sine is sine to the minus 1. Okay, so I need to take the inverse sine of this number. That's what we need to do to finish the problem. So I hit second and then the sine key, which gave me sine to the minus 1, so that's how that appears. And then I just wanted to do it to this number. And I'm not sure how many of you use the answer button on your calculator, but it's really helpful. It just allows you to take the answer that you just got and plug it into something. The way you do that is you hit second and then this key down here where it says A and S for answer. So you just do that, hit enter, and there's our answer. Okay? So again, once I've gotten this number calculated, I would do second sine and then second answer and hit enter, and I get my answer of 28.9 degrees. Okay, one more practice problem. Let me talk about it and then I want you to pause the video and see if you can get the correct answer. Now notice the light is coming from the water. Some of that light, as it gets to that interface, will be reflected back into the water. So this is now theta 1. This is theta 1 prime. And some of the light will come out of the water into the air, and that's theta 2. And so we're trying to find theta 2 and theta 1 prime. Why don't you pause the video and see if you can follow the steps we just went through to get the answers. Okay, how did you do? Well, first of all, the angle of reflection, that's easy. Theta 1 prime is just the same as theta 1, and so theta 1 prime is going to be 20 degrees. Okay, so again, that's always easy. But now, let's see if we can solve for theta 2, the angle of the light in the air. In order to do that, I'm going to start with Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. And notice that once again we're trying to solve for theta 2. So I'll divide both sides by N2. Therefore, sine theta 2 is equal to N1 sine theta 1 divided by N2. Sine theta 2 is equal to N1. Now here you have to be careful. We're starting in the water and we're ending up in the air. So sine theta 2 is equal to N1, but that's the water. So that's 1.33 times the sine of theta 1, which is 20, divided by N2, but that's air, which is 1. Okay, when you calculate that, what you should get is sine theta 2 is equal to 0.4548867, and then we take the inverse sine to get that theta 2 is 27.1 degrees. So again, what we found is that if this angle is 20, this angle is 27.1 degrees. Here is how I did it on my calculator. So again, notice I just took 1.33 sine of 20 divided by 1, and that's just what we did here. And then that gave me this answer. And then I did second sine, second answer, and then hit the enter key, and that gave me my answer, which I just rounded off to 3 significant digits. Let me just remind you that although we didn't talk about it for sound, this idea of sound waves changing direction at an interface from one medium to another is exactly the same as for light waves. So this is very relevant to ultrasound, that we always get some of the sound reflected as well as some of it transmitted or refracted. All right, that is the end of our video today.